In physics, we frequently find ourselves confronted with the situation where more than one force is acting on an object, and so we have to find the net force acting on that object. We can take advantage of the vector nature of force to utilize vector components to find that net force, and we shall do so in this example. The problem statement is two people are trying to use ropes to pull down a tree. One is pulling with a force of 125 newtons in a direction 42 degrees south of east, and the other pulls with a force of 227 newtons in a direction 32 degrees east of north. Question is, what is the size and direction of the net force exerted by the ropes? Step 1 in the problem-solving process involving net force is to draw a diagram showing the forces which are acting on the object, in this case, the tree. These diagrams do not have to be great works of art. They simply have to include some representation of the object, and for the tree we can utilize a dot, and then drawing the forces going in approximately their proper directions. You don't have to use a protractor for this, just have it going in roughly the correct direction. So our first force, F1, is traveling south of east at an angle of 42 degrees, and we're going to label that F1 as a magnitude of 125 newtons. The second force is at an angle of 32 degrees east of north, and so we draw it like so, with an angle of 32 degrees, and we label that F2, and it has a magnitude of 227 newtons. And so we've completed step 1, drawing a diagram showing the forces acting on the object. Our second step is to establish a coordinate system. In other words, to say, what do we mean by x and y? What do we mean by positive and negative? And in this situation, we can do a fairly standard definition where x is horizontal and y is vertical. Since it's pretty apparent that the net force is going to be in that direction, in other words, east, we can call east positive and save ourselves a little trouble. The vertical direction is more arbitrary because one vector has a southward component, another vector has a northward component, and so arbitrarily we will assign the positive direction to upward or north. And so we've established our coordinate system. Step 3 is to ask the question, given this coordinate system, do any forces need to be broken up into components? If so, draw those components and develop formulas for those components. Well, in this case, we certainly do have both forces with x and y components. We look here at F1, we see that it has an x component, a horizontal component, which we shall call F1x, and it has a y component, which we'll call F1y. Note that x and y, as always, make a 90-degree angle with each other, so we have a right triangle. Similarly, when we look at F2, we can see that F2 has two components. It has a northward component, which we shall call F2y, and an eastward component, which we shall call F2x. Once again, realizing the two components make a right angle. So having drawn the components, we now turn our attention to developing formulas for those components. For that, we use the trigonometric functions. In this first triangle involving the components of F1, we see that the angle theta is 42. So we begin with the sine function, the sine of 42. The sine function is opposite over hypotenuse. Looking at this triangle, we see that the side opposite the 42-degree angle is F1y, and that the hypotenuse is the force itself, F1. Notice at this point I'm not plugging in numbers yet. We'll save that until the last, just in case we get lucky and something cancels out. To eliminate the fraction here, we multiply both sides by f1, and that gives us our first formula for the y component of f1 sine 42. Turning to the cosine function, the cosine of 42 is adjacent over hypotenuse. Looking at this triangle, we see that the side adjacent to the 42-degree angle is f1x, so that goes up here, and that the hypotenuse is still f1. Once again, we multiply both sides by f1 to eliminate the fraction, and we have our formula for f1x, f1 cosine 42. That's our first set of equations. For our second set, we look at this triangle right here. Beginning once again with the sine function, this time the sine of 32 degrees is opposite over hypotenuse. Looking at the triangle, we see that the side of the triangle opposite the 32-degree angle is f2x, and that the hypotenuse is f2 itself. As before, we multiply both sides by f2, and we get that f2x is f2 sine 32. f2x is f2 sine 32. And finally, we look at the cosine function. Cosine of 32 will be adjacent over hypotenuse. We see that the side adjacent to the 32-degree angle is f2y, that the hypotenuse is still f2. Multiplying both sides by f2 gets us our final formula for a component, the y component of f2y, which is f2 cosine 32 degrees. And step 3 is complete. We have drawn the components, and we have developed formulas for the components. Step 4 in this process is to add together the x components and add together the y components, making sure that we take note of their direction. Looking first at the x components, we see here on our diagram that there are two x components, f1x and f2x. So when we go to add up the x components, we say, all right, f1x is to the east, that is positive, so it gets a plus sign. f2x is also to the east, so it also gets a plus sign. And so the sum of the forces in the x direction is going to be, looking over here at our equations, f1 cos 42 plus f2 sine 32. Now it's time to plug in some numbers. F1 is 125 newtons, and F2 is 227 newtons. Remember, since they're both to the east, they're both positive, so we add them together, and we find that the net force in the x direction is 213.18 newtons. Notice that this has more significant figures than the problem. The problem has 3 significant figures, but since this is an intermediate calculation, I'm keeping a couple of extra significant figures. Now, turning our attention to the sum of the forces in the y direction, we see that there are two y forces, F1y, which is downward, F2y, which is upward. Since the directions disagree, they're going to have different signs. And we take a look here at F1y. It is down, south, which we have called negative. And so we put a negative sign in front of F1y. But F2 is upward to the north, which we call positive. So it gets a positive sign. So really, we're subtracting these components as we combine them. Once again, we turn to our formulas. We look over here and we see that's negative F1 sine 42 degrees plus F2 cosine 32 degrees. Plugging in the numbers and determining the sum of the forces in the y direction, we get 108.87 newtons. Now this is significant to look at these components because we see that the net force in the x direction is positive, so the net force will be to the east. That is not a surprise. But we look here at the net force in the y direction. That is going to be positive, and so the net force is going to be northward. So if we were to draw in the combination of these two vectors, the net force, we would realize that that net force is going to be roughly in that direction. Because this component of the net force, sum of the forces in the y direction, is northward. So immediately we have a rough idea of what the direction of that force is going to be. As to the size of the force, we can now turn to the Pythagorean theorem, saying that this force right here is the hypotenuse of the triangle, and the two components, the x force and the sum of the forces in the y direction, are the two sides of the right triangle. Plugging in 213.18 for sum of the forces in the f direction, plugging in 108.87 for the sum of the forces in the y direction, and then taking the square root of that sum, gets us the net force in the x direction, which is 239.37 newtons. We would report this as 239 newtons because the problem has three significant figures. As to finding this angle right here, this angle theta, the angle that the net force makes with the horizontal, we would turn to, for example, the tangent function. There are many ways to get about it, but this is probably the easiest. The tangent formula is opposite over adjacent. And in this case, we note that the component opposite the angle theta is the sum of the forces in the y direction. The adjacent will then be the sum of the forces in the x direction. Taking 108.87 and dividing by 23.18 gives us a figure of 0.51. We then find the angle theta by taking the inverse tangent of 0.51, and that gives us an angle of 27 degrees. And so for this problem, our final answer would be that the net force acting on the tree is 239 newtons in a direction 27 degrees north of east.